Okay, so in this video I'm going to talk about the proof of Napoleon's theorem using rotational homothety. So in the previous video I proved Napoleon's theorem, but the proof was the proof was based on the construction of the construction of the first Fermat-Torricelli point of a triangle, and finally the proof was using the angles. So we proved that the angles of the triangle are equal to 60 degrees, and because of that, from that we concluded that it's equilateral. So here I will prove directly that the sides of this triangle are equal to each other. So recall that we have an arbitrary triangle. We consider the equilateral triangles constructed on the sides of this triangle, either to the inside or to the outside, but for now we are going to consider to the outside. So like this, like this, and like this. So three equilateral triangles, and we consider the centers of these triangles, and Napoleon's theorem claims that these centers form itself an equilateral triangle. So once more, the original triangle is arbitrary. It can be any triangle, and still this triangle formed by the centers is equilateral. So denote the points. This is PQR, and denote the centers by X, Y, and Z. Yeah, so in the previous video, the proof in the previous video was we proved that the angles of this triangle are 60 degrees, and from that it follows that it's equilateral. So here we are going to prove that the sides are equal, not just that the angles are equal. So we consider so consider these segments, and we consider the rotational homothety. So we consider rotational homothety with center C, and the ratio with center C and ratio equal to, well, whatever, like this, I guess it's square root of 3 or something like that. I think it's the square root of 3, but basically the ratio of, so let's put it more more accurately as it doesn't matter what the specific value is, but the ratio of the radius of circumcircle of an equilateral triangle to the side of this equilateral triangle. So it doesn't matter actually what the specific value of it is, if it's square root of 3 or any other value. Like, it's clear that, like, if we have an equilateral triangle, then the radius of the circumcircle, basically from the center to the vertex, basically this radius to the side, so R to A, and this does not depend on the scale of the triangle. So, like, if you take another equilateral triangle, this ratio would be the same because they're all similar to each other. Yeah, so the specific value doesn't matter. So we notice immediately that this ratio is equal to Cx over Cb, and also Cy over Cq, right? So Cx is the radius of the circumcircle of this equilateral triangle, and Cb is the side of this triangle, and Cy is the radius of the circumcircle of the bottom equilateral triangle, and Ca is Cq, well, both Ca and Cq. Cq is the side of this triangle. So, and center C ratio and the angle, so the rotation by angle, angle is 30 degrees counterclockwise. So basically we rotate here and here, and notice that under this rotational homothety is just a composition of a homothety and rotation. So under this rotational homothety, the triangle, so C stays, so the point C stays in place. The point X is mapped to the point B, and the point Y is mapped to the point Q, because so this angle is 30 degrees, of course. This angle is also 30 degrees, and so the line Cy is mapped to the line Cq, and the ratio, like, is chosen in such a way that not just the line Cy is mapped to Cq, but Y itself. So the segment Cy, the length of this segment is mapped to the segment Cq, so this ratio. And similarly here, so Cx, the length of Cx, so first the line Cx is mapped to the line Cb, and the length of Cx is mapped to the length of Cb, so therefore just the segment Cx is mapped to Cb. So from this we conclude that in particular that the triangle XCY is mapped to the triangle BCQ. But yeah, like actually we don't need the whole triangle, but like what we need is just the segment. So yeah, we don't even need the point C here. We don't even need here this. So only from this we conclude that the segment XY is mapped to the segment BQ, right? So like under rotational homothety, like line is mapped to a line, like segment is mapped to a segment, right? So so if the point X is mapped to point B and point Y is mapped to point Q, then the whole segment XY is mapped to the whole segment BQ. So in particular, this means that the ratio of the length of XY to BQ is equal to the ratio of the homothety. So the ratio, let's denote it by some denoted by so R is usually used for the radius, so let's use K. So let K be this ratio. Like again, it's like it's a specific number, like either square root of 3 or whatever else. Like it doesn't matter what is this number, but it is a specific number. So so the ratio of these segments is equal to K. So that's what we proved. Now similarly we can consider on the other side. So the rotation with center A and these segments. So basically the rotation here by 30 degrees. So this is also 30 degrees angle. So the rotation around rotational homothety around point A by 30 degrees with the same ratio, right? So then so another rotational homothety with center A ratio, the same ratio K, and angle 30 degrees. So then similarly we get that the point Z is mapped to the point B and point Y is mapped to the point Q. So under this rotational homothety, Z is mapped to B and Y is mapped to Q. And from this we conclude that the whole segment ZY is mapped to the whole segment BQ, right? And from this we conclude that the ratio of ZY over BQ is equal to the ratio of the homothety K. So now we notice that so we compare this and this. So when we compare these two results, this and this, we notice that we have two ratios that are equal to K, and in the denominator there is the same length PQ. So it follows that in the numerator also must be the same length. So xy, the length of the segment xy must be equal to the length of the segment zy, or like, let's write it as yz. Alright, so xy is equal to yz. These two segments are equal. Well, and so similarly we can prove that the like choosing rotation around point B, rotational homothety around point B, and so we map zx to AP, and here we around rotational homothety around C now clockwise. Yeah, here I also forget to say that angle is 30 degrees clockwise. It was clockwise. So yeah, so basically like we proved that the two sides of this triangle are equal to each other, xy of the triangle xyz. So because of the symmetry of the whole picture, like without loss of generality, we can say that the third side is equal as well. Like, or we can say that similarly by considering the rotational homotheties around point B and C. So around point B, by like by mapping zx to AP and by mapping yx to AP, we proved that they are equal to each other. That zx is equal to yx. Yeah, so the third side must be also equal. And that's how we prove this using the rotational homothety. And the angles, by the way, also we can also conclude the angles between. So we concluded that the length of xy and yz are equal, but we can also calculate the angle, this angle between these two segments, because under this rotational homothety, so because xy is mapped to BQ, so this means that the angle, so this means that the angle between the lines xy and BQ is equal to 30 degrees, because that is the angle of the rotational homothety, and here as well. So from this it follows that the angle between zy and BQ is equal to 30 degrees. And now, knowing this angle and this angle, we conclude that, so let's write it here. So from this and from this, we conclude that the angle between, so because BQ is the same, right? So the angle between xy and, let's write yz, the lines yz is equal to 60 degrees. The sum of these angles. Yeah. So this angle is 60 degrees. Yeah, so this concludes the proof. Well, so let's write, so similarly, so we proved this, let's write it similarly. Similarly, we can prove that zx is equal to xy, and then we have that xy is equal to yz and is equal to zx. All three of them are equal, and this concludes the proof. Yeah, so that's it for